Hey, what's going on, everybody? My name's Ryan. I'm going to be tutoring with physics today, and I'm going to be focusing on the basics of kinematics. So, talking about distance, velocity, acceleration, what scalars are, what vectors are, and how to look at those graphs and go between them, the relationships there are, and how you can connect that to the formulas to help you really understand what these concepts are that for the rest of physics you'll be building off of. As I mentioned on my screen, I do a tutoring service, and if you'd like to learn more about it, I have my website in the description of the video. Let's get started. So in physics, we talk about distance a lot. That's a word you'll hear thrown around. And an example of a distance would be something like 5 miles. It's pretty clear you have a number, and then you have a unit next to it. And together, that gives you your distance. Distance is known as a scalar quantity because it doesn't tell you how that distance was moved. It just tells you what distance was covered. Instead, we also have displacement, which goes hand in hand with distance, and that is a vector. And before you get confused, a vector is something that is very similar to a scalar. It just has direction. That's the biggest thing. So that would be like if I said 5 miles north. It's the same thing. We have a magnitude, a unit, and we have a direction. And that's how you relate these two, distance and displacement. Now, as an example, if we had a person who went 9 miles this way to the right, and then he went 5 miles back the other direction. So first he goes 9 miles to the right, and then he goes back to the left for another 5 miles. He would have covered a distance of 9 plus 5, which is 14 miles. Now, you might see where I'm going with this. When you start analyzing displacement, you have to take into account that this is actually negative 5 miles if we're assuming this is positive 5 miles. A good unit to figure out, like a good way to determine if something's positive or negative, typically if it moves to the right or up, it's considered positive, and otherwise it's considered negative. So we're going to assume 9 miles to the right is positive and 5 miles to the left is negative here. And that ends up getting a 9 minus 5, which is 4 miles net difference. And net is really important when you are talking about physics. So here we're going to talk about 4 miles to the right from the start point. Now it's important to remember that in both cases, this distance that's covered, the path that's moved, not the distance, the path that's moved is the same. But these two different ways to measure it, distance and displacement, are different. In distance, we have a total path of 14 miles, but in displacement, we just have like a picture before and a picture after, and then we say that's 4 miles difference, 4 miles net difference to the right, which could also be written as 4 miles positive if we're using the scale of to the right is positive. Next, we have speed. So we talked about miles. That was our unit for distance. For speed, we're going to have something similar, but it's 5 miles per hour. That's what your speedometer is for your car, right? And so what that's saying is miles per hour. So you're traveling actually 5 miles every hour. So that would be if you're running and you're running 5 miles per hour. Every hour that goes by, you're gonna have covered 5 more miles, as long as you're covering the same speed, or as long as you're the same speed throughout that whole time. And if we look at this more carefully, we'll say that this is 5 miles for every 1 hour. And that's our speed. But this is a unit of distance on the top in the numerator, and this is a unit of time in the denominator. So you could also say that speed is your distance divided by your time. And that's something you'll notice throughout physics is that it's really important that you write your units whenever you're talking about something, because that can help you determine what formulas have gone into creating that thing. So we have distance, and the unit is miles over time, which is hours, and that gets us our miles per hour unit. Now, similar to distance and displacement, we have velocity, which is very similar, but this is the scalar form, which remember that means no direction, and velocity is the vector form, so that has direction. And we said before, on this side, we had distance as our speed measurement. That's our distance. But on this side, on the right, we're going to have 5 miles per hour, just like before. But now we're going to have positive, or that could even be 5 miles per hour negative. Both of those are velocities because they have direction. And in order to get your velocity, you have to use displacement to calculate your speed. So I'm going to move this to the bottom here as your formula. And over here, instead of using distance, we're going to use displacement over time. And that gets us our velocity. So I'm going to erase a little bit here, and I'm going to do a little example of what that could look like as far as differences. So again, we have our person. He runs 9 miles this way to the right, and then he runs 5 miles to the left. And that's all done in the time frame of 1 hour for that whole path. So if you looked at his speed, we would say his speed was 14 miles, because remember, you're using distance, not displacement. 14 miles were covered in that hour, so his speed is 14 miles per hour. But if you look at his displacement, we would say that displacement was only 4 miles covered in that hour, because you went 9 miles positive and then he went 5 miles negative. So we get 4 miles per hour as our velocity. Again, it's the same example, same person running in both cases. He's running this way, then he's running back. But the two ways to measure that movement are your speed or your velocity. So what that's saying is that although his speed was quite fast, 14 miles per hour, it was the same as if somebody moved directly from start to finish right here in just 4 miles per hour. So as long as you take the more direct route, your velocity can be lower as opposed to somebody who took a less direct route and their speed was higher. So now we've talked about distance, we've talked about speed, and then we've talked about their vector forms also. I want to talk about acceleration. So acceleration, before we get fully into that, we should talk about reminding people what the units were for the distance. We had units of meters or miles. For velocity, we have units of meters per second. And that's just saying how much distance, which was in this case meters every second, were covered. And now for acceleration, we're going to go one step further. And I'm going to say this is meters per second squared. And so what we're looking at now is instead of every distance per time, we're going to look at distance per time over another period of time. And to put that in example form, that would be meters per second every second. If that's a little bit confusing, don't worry. I'm going to show you a table in a second that helps explain it a little bit better. But it's important to note that as you get further down the line, velocity is really describing how your distance is changing. And acceleration is describing how your velocity is changing. So I'm going to do a little example, and that should help out with explaining what's changing with the table. I'm going to compare also the formulas. So we said before that if we looked at your velocity, we said that was your displacement or your distance, your net distance over your time, which is the same as position final minus position initial over your time. So remember how we had the little guy, he ran this way, then he ran back. We would say that the initial position was right here at the start, final position is right here. So his displacement or his distance final minus his distance initial was in that example 4 miles. So you'd plug in those numbers into the formula on the bottom, and you'd plug in your time, and that's how you get your velocity. Similarly, when we're calculating acceleration, we have to look at your change in velocity over your time, which is your velocity final minus your velocity initial over time. And that's an important distinction to make, is that these two equations are not that different after all. As you go meters every second, that's still the same as distance, which is in meters every second, which is why time is in the denominator. And then meters every second is we're plugging in meters per second here, and we're plugging in here seconds. And when you divide the two as far as your units go, you end up here with meters per second every second, which is meters per second squared. So let's go and use a table as an example. I should clear things up a little bit more because it's a little bit more real world. For our first example, example 1, I'm going to say that we have a constant velocity of 5 meters per second. And so if we made a table with t as our time, and that's every second, and distance, and that's in meters, we would have this right here. 0, 1, 2, 3, 4, and you'd go on so forth. Our distance, which is changing every second, we'd say, okay, 5 meters per second. So we started at 0. 0 seconds have passed, so we're still at position 0. But this little person is running at 5 meters per second. So his distance covered after 1 second is 5 meters. After 2 seconds, 10 meters, 15, and 20 meters for each of those corresponding times. We could say that his distance covered is equal to his velocity times his time. And that works out as far as units as going his distance in meters covered equals his meters per second times his seconds that have been passed. And that cancels out. And we can verify, yep, that makes sense. The units all work out there. Oops. And that's how you can verify that your equations are right and what you're plugging in is correct. So we've canceled out the S and the S for seconds, and you're left at with meters equals meters, and checks out. If I multiplied any time by the 5 meters per second, I could determine how much distance had been covered by that time. We can also do the same with a second example. If we said acceleration was 5 meters per second every second, or 5 meters per second squared. A little cram there, but that's okay. And in this case, he is going this way and he's speeding up. So he's boom, boom. He's covering more distance as time passes. So maybe he covers just a little bit at first, then he covers a little bit more, and then he covers much more because he's speeding up. It's like a car accelerating. So we look at t in seconds. And in this time, we're going to look at velocity in meters per second. And do the same thing. 1, 2, 3, 4. So we're saying his velocity is changing every second. So his velocity starts at 0 because you're starting at rest. And his velocity goes from 5 to 10 to 15 to 20. And we can do the same equation and say that your velocity is equal to your acceleration times your time. And I'm going to prove that formula to you by saying that if my acceleration is in meters per second, every second, and my time is in seconds, those two cancel out, and we're left with meters per second equals meters per second. That proves that that equation is true. And so at any time, if I know the acceleration is still 5 meters per second, I can tell you what the velocity would be. I'm going to draw that out here. For that example, which is still example 2, continued, we have somebody whose acceleration is 5 meters per second. Oops. In that picture, he starts out covering just a little bit of distance because his speed is still slow. And then after 1 second, so this is 0 seconds, this is 1 second, he's going to cover a little bit more. And then at the 2-second mark, he's going to cover more. And then at the 3-second mark, he's going to cover a lot more. So this is 1 second. This is 2 seconds have passed. This is 3 seconds have passed. This is 4 seconds have passed. And this is how much distance has passed. So the bottom is seconds. The top is still in meters. So that's your car accelerating in a straight line. Nice. So let's move on to example 3. Example 3. And in this case, we're going to have a little car that has velocity of 10 meters per second to the right, positive, and an acceleration that's actually negative, or an acceleration to the left of negative 5 meters per second. So I'm going to use the same strategy, go with the table, and I'm going to have t of time of seconds, velocity, which is meters per second, and speed, which is still meters per second, no direction. It's your magnitude or your scalar form of velocity, so we're not concerned with direction. And I'm going to draw some lines here so it's a little bit easier to see. So if our time is 0, 1, 2, 3, 4, 5, we're starting with 10 meters per second positive velocity. That's our initial velocity. So I'm going to put V naught, V0 right there. So that's what the velocity is at time equals 0. And if the velocity is 10, then the speed should be 10 because we're just scrapping the sign. But the velocity is changing by -5 every second. So we went from 10 meters per second to 5 meters per second to 0 meters per second, so we stopped for a moment. And then -5 meters per second, -10 meters per second, -15 meters per second. And then on the right, remember your speed is your velocity without the sign. So we have 10, 5, 0, 5, 10, 15. We're just scrapping the sign. Okay, so now we have a little car, and he's going this way at 10 meters per second. So 1 second has passed, 1 second, Then he's gone this way at a lot less velocity. 2 seconds have passed. And he is now right at this point. He's at 0 meters per second as far as his speed goes, or his velocity and speed. This is his velocity. He's at 0. And he's covered quite a bit of distance going this way, right? But now we look at, okay, what happens at 2 seconds? Well, he starts going negative. So he's going to cover the same distance that he covered going this way, but he's going to cover it the opposite direction now that he's moving negative. So we have the dot there, and then we have the dot right here. And so I'm going to change colors so you can see it a little bit better. This is still at 2 seconds. This is at 3 seconds. This is at 4 seconds. And it turns out we have to actually shift our number line because he is now accelerated to the point where he's moving pretty fast in a different direction than we had originally been going in. So he's covered some distance to the right, and now he's covered some distance back to the left. And his displacement actually ends up being further left than when we originally started. Something to write down is that in most cases, or in all cases, if acceleration and velocity are two cases here, we have the same sign, then you're speeding up. So that means if we are moving to the right and we're accelerating to the right, that means we're speeding up over time. And those little dots of position that I showed you are changing and getting bigger and bigger over time. More distance is being covered over time. But if they're different sign, then you're actually slowing down. So if velocity is to the right, like we had in that last example, but acceleration is to the left, well, then we're going to be covering less distance per time because we're slowing down. But then we're going to end up speeding up the other direction. Remember, the distance between each of these dots is showing how much distance was covered in a certain amount of time. So the bigger the distance between those dots means the higher velocity that that car had at that point. So for the blue path, we are slowing down because our velocity is to the right, but our acceleration is to the left. That's why this is negative. And then for the orange path, we're speeding up because our velocity is to the left and our acceleration is to the left too. So that's an important note to make. You can help see that in the speed. Here we're speeding up. Our speed is getting bigger, but up here for this section, we're slowing down. And that's why the speed is decreasing. And that is reflected again with the time that's being covered here. So let's move on. Now I want to talk about graphs and how we can relate, your position, velocity, and acceleration graphs. So to start out, I'm going to start out with our position graph, which is in meters, and our velocity graph, which is in meters per second. So now that I have our graphs made, we have time on our x-axis, and that's in seconds, and time on our x-axis for the velocity graph, and for the y-axis, which is this, we have position in meters, And over here we have velocity, which is in meters per second. And I'm going to tell you how you can relate these two graphs together. So if we have a graph and the position is changing in this way, then let's suppose we have 10 meters right here, and this is after 2 seconds. Therefore, this would be, if the graph is linear, which we're believing it is, negative 10 meters, and 4 seconds have passed at this point. So if you want to find out what the velocity is at any point on the position graph, you have to look at the slope. So we look at the rise and the run. Remember, that's how you find slope. So boom, boom. If the rise of this triangle, this edge right here, is 10 meters, and the run is 2 seconds, then we can calculate that to be 5 meters per second as the velocity. And remember, that goes back to our formula of distance over time. And so that would indicate that if the slope is the same at any point along the graph, boom, 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 then our velocity is 5 meters per second throughout the whole graph. But something important to note is that it's not 5 meters per second. Our speed is 5 meters per second, but our distance is actually negative. I should have said displacement here. Fell for the oldest trick of the book. And our velocity is therefore also negative because we're moving further and further negative in our chart here for the position graph, further and further negative. So if that's the case, then our velocity is just constant throughout that whole time at negative 5 meters per second. And since there's no change in velocity, that means our acceleration is 0 because there's 0 meters per second change every second. And then now let's look at a little more complicated of an example. If we have, again, the same graphs, we have position up here, and then we have velocity and acceleration. And our distance unit was meters. Velocity is meters per second. And we said that our acceleration is change in velocity over time. So meters per second every second, meters per second squared. And that's our axes. This one goes here with your meters. This one goes here with meters per second. This one goes with your acceleration, meters per second squared. If we have a situation where our distance or our position graph looks not linear anymore, it's more curved, we still have to look at the slope of every point, but that gets a little bit difficult. You can't just do rise over run like you were able to before. Instead, we have to use more qualitative words instead of quantitative. Qualitative being describing what is the shape looking like. If I drew a parallel line right here, this is pretty steep, gets less steep, and ends up being 0 here. So I'm going to make some notes on this graph. This is very steep and negative. This is less steep, negative. And this is not steep at all. In fact, it's actually flat for the slope there. So I'm going to say a slope of 0. So then I can go, okay, if a very steep negative, and that's my slope, and I said velocity was my slope of my position graph, then I can start out pretty negative right here. I know it's less steep, so there's going to be a point somewhere closer to the x-axis, and then at this last point, we said this was 0, so our velocity is 0, because our position is no longer changing over time. Now, do I draw a curve? Do I draw a line? Well, that's where you got to look at what is the shape of this top graph. The shape of the top graph kind of looks like a parabola if it was stretched out. And you can draw a parabola with x squared. That's a parabolic shape. But then as you go down here to velocity, we have to say that our velocity, which is the slope or derivative, remember derivative and slope are the same thing. We take the derivative of this position graph, which was x squared, we'll get something linear. So if you take the derivative of x squared, you would get 2x, and we're not really concerned with this 2, so I'm just going to say it's x for now, as far as the shape of the graph, which means that this should just be a normal line, like that. And then if we take the slope of this graph, of the velocity graph, and compare that to our acceleration graph, well, we said acceleration is the slope of velocity, and velocity is the slope of position. So you take one more derivative, you would get a constant number. Therefore, the slope is constant, which does check out with what we do when we look at rise over run. Now, if we suppose that this was 10 meters per second, and this was 2 seconds, and if we're going, remember this is negative 10 meters per second, if we're going more and more positive every second, because our velocity is changing, and our velocity is increasing, that we look at the slope, we'd say v final is 0 minus v initial is 10, which is actually 0 minus negative 10 meters per second every second. We would get 0 minus negative 10, and that gets us positive 5 meters per second every second. Because again, this is meters per second in its unit. So that gets us a constant flat line right here. And this is what the example of we're starting out with a negative velocity and we're accelerating positive. It's kind of similar to that last example where we said that something was moving in one direction and accelerating the opposite direction. The center of the plate slows down. But in this case, we just stop the video right when it hits 0 velocity, which is when our position no longer stops changing and we're staying constant at the 0 point. So I guess for this one, if we were to draw it out, it would look something like we are starting at the origin, but our little guy is way out here, and he is moving pretty fast this way after 1 second, slightly slower, slightly slower, slightly slower. I drew too many dots, but what I'm saying is that he is moving to the left with initial velocity, but his acceleration is to the right. Therefore, he's slowing down. And then we stop the video right when he hit that middle, the origin, which is right there. So in summary, I'm going to just cover what we learned today. We said that distance is a scalar form of displacement. And what that means is that scalars don't have direction. So again, we have 5 miles, and then we have 5 miles north here. Those are important because they help describe the same motion, but in 2 different ways. We can see more about which direction everything is moving in. The same goes for speed and velocity. Speed is a scalar, velocity is a vector. Therefore, if a vector is to be calculated, you need to use the vector form of position, which is displacement. And that'll get us positive or negative 5 meters per second, 5 miles per hour, whatever it may be. And these are the formulas that we use for that. If we have distance and we want to describe how distance is changing, we talk about velocity. If we want to try to describe how acceleration or velocity is changing, we have to talk about acceleration. And that's because velocity covers how many meters are covered every second, and acceleration talks about how many meters per second are covered, or is the velocity, and how is that changing every second. We use these 2 equations to help describe that. Here are 2 examples. In this example, we had a constant velocity, and so our distance was changing in a linear fashion. And then here we have our acceleration, which is constant, and so our velocity was changing in a linear fashion. Here's an example of a movement of example 2 right here, where we had a acceleration of 5 meters per second. We were getting faster and faster and faster, each of these lines being what was covered in 1 second, the distance covered in it, 2 seconds, 3 seconds, 4 seconds. And then here we have example 3, which is where we're talking about velocity and acceleration not being in the same direction. This is positive, and then this is actually negative here. And so you have to slow down for a bit before you can speed up going the other direction. This is a really important note about that, and that's reminding you that velocity and acceleration have to be in the same direction to be speeding up, and different directions, that means you're slowing down. And then looking at these graphs, we said that position graph will help model our velocity graph by looking at the slope. And if you look at your equations, and that's our distance over time dot also velocity, that goes back to the equation I talked about right here. Distance over time, delta distance over time dot its velocity. Then for this other graph, we have our position, velocity, and acceleration. In this case, we had h squared. If we took the slope of that, or the derivative, we got a linear form of x. And if you take the slope or derivative of x, you end up getting with a constant number. And that's how we can model and work from position to velocity to acceleration again. Cool. I hope you guys learned something today. I won't lie to you guys that physics is tough, but with the right teacher, some one-on-one tutoring, and some flexible scheduling, you can get ahead of the game early, get that help you need as you go, rather than try to learn it all at the end. It's important that you're learning throughout physics class because it just builds on top of itself. It gets wilder and wilder as you go. I'd like to say that physics is fun once you get the hang of it, but it's not super easy to get the hang of, and that's what I'm here to help you with. You're capable of great things, and now it's time to prove it. Follow my website down below in the description if you want to schedule a session. We can make that happen. Have a good one.